Welcome to the 9th tutorial of the RISC-V Architecture and Assembly Language series. In this session, we're going to examine some of RISC-V's vector capabilities. Note that not all systems support vector operations. On the hardware side, the Banana Pi BF3 is capable of running all the programs covered in this tutorial. Spike also supports vectors for those not using hardware-based single-board computers. Some of you may already be familiar with SIMD instructions. In the example shown, a single add instruction manipulates 8 pieces of data. So we have a single instruction working with multiple pieces of data. The pieces of data are known as elements. And with RISC-V architectures, they can vary in width. For example, each of the 8 elements shown could be 32 bits wide. The advantage that RISC-V holds over many other implementations is that the number of elements in a vector register is not fixed. An example configuration could be 16 elements that are 16 bits wide, 8 elements that are 32 bits wide, or even 4 elements that are 64 bits wide. This implementation would hold a total of 256 bits. The program, however, does not need to know in advance the total number of bits that a vector register supports, and this will be demonstrated with the example programs shown. This bit capacity is implementation dependent and is termed VLEN. The reference document is the RISC-V Vector Extension version 1.0, and it can be obtained from the link shown. Before starting out on our journey, ensure that vector support is available by running the listed code. To assemble, use AS-M and O-relax-M arg equals RV64GCV-G-O. Then followed by the file name.o, followed by the file name.s, and this will assemble it. Link it simply by doing LD-O with the file name of the executable and then file name. .o. To link it, this program will print out a text string denoting if the system in question has vector support. If it does not have vector support, an illegal instruction will be encountered. We've seen earlier on Linux-based systems how to tell the processor's capabilities. Here, the string RV64IMAFDCV denotes vector support as there was the letter V present in the string. Similar to the integer X registers, there are 32 vector registers. The vector registers each contain a fixed number of bits known as VLEN. VLEN is implementation dependent, but it must be a multiple of 8 and no greater than 2 to the power of 16. Each vector register is divided into a number of elements similar to an array. The number of array members is dependent on how many bits each member has. The greater number of array members, the smaller the width available in bits of each element. This element width is chosen by the programmer and is termed the selected element width, or SEW. The number of elements available in a vector register is equal to VLN divided by SEW. So VLN is equal to 256 bits, and if the selected element width is 32 bits, then it's 256 divided by 32, which equals 8 elements available. The layout of the vector registers for a system with a VLEN value of 256 bits per register is as shown. The lowest element occupies the least significant bit values, and the most significant element will occupy the highest bit values. Here, the layout corresponding to a VLN of 256 with an SEW of 32 will have 8 elements available. Starting with n equals 0, element 0 occupies byte 0 through 3, or bits 0 to 31. Element 7 will occupy bytes 28 to 31 or bits 223 to 255. The next layout shows 4 elements. However, These are 64 bits wide. Finally, two registers grouped together. Using a setting known as LMUL with the combined logical register holding 16 elements with each element being 32 bits in width. The LMUL value can have integer values of 1, 2, 4, and 8. Fractional grouping is also possible, such as an LMUL value of a half. There are a number of control and status registers associated with vectors. The last four are important for our purposes, and GDB will be used to view their status. These registers are not typically manipulated directly, but are set as a result of vector configuration instructions. The values can be read and placed into regular scalar registers. The vector length register known as VL contains an unsigned integer specifying the number of elements, and will be used to verify the instructions as the code examples are executed. Understanding the V-type register is extremely important, and it denotes the selected element width of the element values for the vector configuration as shown in the tables. In addition, it shows how the mask and tail elements should be treated. A tail element is an unused element. For example, if we only need to process 6 elements of an 8-element configuration, the last 2 leftover elements are termed tail elements. A policy can be set up so they retain their previous values or adopt a don't care policy. These policies are termed undisturbed and agnostic respectively. Mask elements are covered later in this tutorial. The illegal bit is the highest bit, so it'll be the vlen-1 bit. To reiterate, each logical vector register by default maps to one physical vector register. Each vector register's capacity is fixed at vlen bits. The number of elements is determined by the width of each element selected element width. The grouping is determined by LMUL, which changes the one-to-one correspondence of logical to physical. If we look at more of the vector CSRs that we haven't discussed so far, one is VLNB, which is the vector byte length register and has the value VLN divided by 8. Seeing as VLN is expressed in bits, this one will be just expressed in bytes. Again, it's a design implementation, so it can vary by manufacturer. VLMax is defined as LMUL multiplied by VLEN divided by SEW. The configuration command vsetVLI is a key vector instruction, and we'll look at that in some detail. This is used to configure the vector registers. One example is vsetVLIT0T1E32M1TAMA, which sets an element length of 32 bits as shown in the string with the grouping factor of 1. That is the parameter M1 with agnostic tail and mask attributes. That's the TA and the MA. The application vector length, AVL, is requesting a length of 64. However, VLMax is given as VLEN divided by SEW, which equals 8. So the rule is if the AVL is greater than the value equal to VLMax, then the VLMax number is returned, which in our case is 8. This is reflected in the value of the register T0. 8 passes will be required to process 64 elements. So what's happening here is the requested value has been stored in source register 1. Here, it's T1. And then the number that has actually been granted will be set into T0. So T0 will contain how many elements can be satisfied by a single pass. This graphic looks a little bit overwhelming, but really it's quite straightforward enough. It shows a subset of values returned in the V-type register according to various vsetVLI requests. So the value that we saw in the destination register is actually reflected in here. So an example is a value of hexadecimal D0, which signifies SEW of 32, LMUL of 1 with the mask and tail attributes set to be agnostic. This chart shows valid V-type values with varying SEW and LMUL fields with fixed VMA and VTA fields. So what we've done here is we've actually set up the VTA and the VMA fields with a value of 1. And then we varied the other fields so you can see what values are legal. Here's an example of a vsetVLI command. This code snippet shows in GDB the results of the CSR registers after the vset-vli command has been executed. The CSR read instructions illustrate how to store the CSRs into the integer registers. The first command returns a v-type value of hex C8 and a vl value of 16. This next example returns a v-type value of hex D8 and a vl value of 4. And the third command returns a v-type value of hex D9 and a vl value of 8. This is twice the length of the previous example since LMUL has a value of 2. Now you can check with the table earlier that your vset-vli commands are accurate because you'll see the value returned in the v-type register as well as the vector length. With vectors there are a number of permutation instructions. In particular we will discuss slide and gather. The vector slide instructions are similar to shift instructions used with X registers. We can perform a vector slide up or vector slide down, which are similar to right and left shifts. The slide operation involves a destination register and the source can be an immediate value or held in a register. When elements are shifted out they are replaced with zeros. With vector gather, we can then extract individual elements from the vector registers, and we can place them into scalar registers or into vector registers as well. So the best way to do that is to look at the programs, and that'll illustrate the mechanism. Okay. Here's our first program. We're going to start looking at how we can add values to a vector. So study the listing here, and then we'll get right onto it. Alright. So we're going to demonstrate the various ways of adding to a vector. So the first thing we're going to do is assemble the program. We're going to turn off linker relaxation, and you can see the architecture switch here. We use the V for vectors. After assembling, we're going to link it. And we're on GDB. So set our breakpoint as normal. Run the program. Now, we're going to load register A0 with the value 8, and this is the number of elements that we're going to configure. You can see that's passed into the vset configuration command. So what happens here is that A0 contains the number of elements that we want. This number will be granted in T0 or as many as the system can give us. The element size is going to be 32 bits. We're going to have a grouping factor of 1. We're going to set our attributes to be agnostic. So, we're going to load A1 with the address of where we have our scalar array numbers defined. And then we're going to store that into vector v1. So if we now look at vector v1, $v1. .w. We can see the words from our scalar array here. So the 8 elements of v1 are set up like that. Now we're going to simply just load a regular scalar element or scalar number into an X register, in this case, T1. We're going to give it the value 5. The first add method that we're going to do is to add the scalar number to a vector. And you can see here that the suffix is vx. So v for vector, x for the regular X registers. We're going to add the scalar register T1 to the vector register v1 and put the results into v2. So we're already seeing the contents of v1. So let's execute that. And now let's have a look at the contents of vector register v2. You can see we've added the scalar value 5 to each of the elements. 3 plus 5 is 8. 4 plus 5 is 9 and so on. So that's very simple. That's just adding a scalar and number to a vector. The next vector addition method is add vector immediate. And the issue really here is with vector immediate. You have very little bits to play with. In fact, there's only a signed 5-bit amount. So this ranges from -16 to +15. Now if you are dealing with very small numbers, you can use the vector immediate method and you can see the suffix here is vi. So vector and then immediate. Here in our example we're going to put the immediate value of 10 decimal and we're going to add this to the contents of register V1. We're going to put the result in register V3. We're already seeing the contents of V1 here, which is 1, 2, 3, 4, 5, 6, 7, 8. So let's execute that add command. And now we're going to have a look at the contents of vector register V3. Here are the 8 elements. We add an immediate value of 10. So 10 plus 1 is 11. 10 plus 2 is 12 and so on. So that's pretty straightforward. The next addition variation we're going to execute is to add 2 vectors together, and you can see the suffix is .vv. We will simply add register V2 and register V3 together and put the results into register V4. Notice there's an error in the comments that should really say V4 equals V2 plus V3. Now let's execute that command. And let's have a look at the contents of V4 in Word format. So if you remember here, we have V1 as this value. We have V2 as this value. We have V3 as this value here. So adding V2 and V3 gives us 6 plus 11 giving 17, 7 plus 12 is 19, etc. So no issues there. The last vector addition we're going to do is to add a floating point scalar value to a vector. The first step we're going to do is load in the floating point numbers that we defined earlier into register A2, which holds the memory address. So now what we'll do is we'll load up vector register V5 with the contents of these floating point values. So let's have a look at register V5. Now you'll see that some of these numbers look a little bit peculiar, and that's because they are in floating point format. So what we really need to do is we'd have to decode them to get back to the floating point values. And there's a number of these decoders online, or you can use AI to see what the converted number is, or consult tutorial 8. What I've done here is I've already encoded this value 400000, and that works out to be the value of 5 in floating point IEEE75 for format. So I've already put that into register T2, and we're going to add that scalar floating point value, and we're going to move into the floating point register FT0. Then we're going to add the V5 values, which we showed earlier, to this register here. And then we'll put the results into register V6. So issue $v6.w. So, again, these are the floating point IEEE formats as well. So you can decode those if you want, and what you'll see is you get an array of 6, 7. A neat trick with GDB helps us further. The command is F for floating point. And then we can put in the vector register and express it in Word format. So there you go. So if you remember back here, we had a value of 5, which we had put into IEEE format, and then we worked with vectors. So this is the values decoded up here as well. So that's the end of that program. Straightforward enough, but these are the different ways you will be adding with vectors. Here's the next program. This will illustrate vslide up, vslide down. So have a look at this first before we start running it through GDB. It should be familiar from the first part of the tutorial. We have already explained the permutation instructions. In this example, we're going to look at vslide. So we'll use the vslide up and the vslide down instructions. And this is really like shifting to the left or shifting to the right within scalar registers, or you could use the terminology up or down if you prefer. So let's use GDB to see what's going on. And we'll set up a breakpoint. We're going to use 8 elements in our vector configuration instruction as well. And we'll load the address of the elements into the memory location A0, which will be pointing to that. Then we'll do vectors 2, so on. Now we're going to configure, as usual, elements with a 32-bit size. We're going to use a grouping factor of 1, and agnostic attributes here as. We will request 8 elements as the AVL value that we require for TAE configuration, and that amount will be granted. In this case, it actually will be returned in T0, so let's look at that. Incidentally, we can have a look at the VL register. So you can actually see that it did return 8. And this is also the value that was returned in T0, which was specified. So let's load that up. And we'll have a look at our V1 register. $v1.word format. And you can see that the elements here are 10, 20, 30, 40, and so on. Let's do the same for the next vector. And we'll look at $v2.w. And you can see that's 1, 2, 3, 4, 5, 6, 7, 8. Now we're going to move the elements in the V1 register 4 places, and we're going to put the result into V3. So you can see when we did the vslide up, we moved over to the right. So these values here went 1, 2, 3, 4 places. So now we have the 10, 20, 30, 40, and we backfilled in with zeros. We're going to do the opposite with V4. We're going to move the elements to the left or downwards. So let's look at that. And have a look at V4. So in this case, we've moved them across. So you can see that we've moved left here, and we've lost elements 1 and 2. They've been slid out, and they've been backfilled with the zeros coming in from the right-hand side. So let's hit next. And next again. So if we look at T2, we'll hold the first element of vector register 3B3. And if we look at T3, you can see it's got the first element here, which was this one. So this is what happens. For this instruction, it takes the first element of the vector. Alright, that's the end of that program. Next, we're going to look at the vrgather instruction. This is slightly different from the previous one where we moved elements around. Here we can extract all of the elements or just particular ones from individual vector lanes. This program will look at the vrgather instructions, and these are part of the permutation instructions that are available. with RISC-V. So set up our breakpoint. Hit run. We're going to have 8 elements as usual. And then we're going to put the value 3 into register T3. We're going to set up the vector values. And we'll do our configuration command. So, again, elements are going to be 32 bits. Register grouping will be 1. With agnostic attributes, we're passing the number of elements into T1. Again, that's the AVL value, and the value will be returned in T0. So I hit next. And if you look at T0 there, you see there's a value of 8. Again, you just look at the vector length register. And that's also 8 as it should be. Now this command, vid, this writes the vector index values into register V0. So if we just look at vector V0 first, you see that it has none of these values in it. If we hit next and then we just bring it up again, you can now see that the indexes have been written. So this is a very useful command for us. Let's load up our vector registers, V1 and V2. And, again, we'll just verify that everything's okay there. Alright. So there's our values, and, again, go in the comments there as well. So what we're going to do here is, in the immediate variant, we're going to look at lane 5. So we're going to look at vector B1. We're going to look at lane 5, and we're going to put that into vector register 3. So if we hit next, and we'll do it again for vector register 4. In this case, we're going to use the value that's held in register T3, which you may recall we put up here as 3. So let's have a look at those two registers. V3. .w. And let's look at vector 4v4.w. So, the first case here. When we looked at the vrgather, we did the immediate value of 5. So if we look at the elements in vector v1, 0, 1, 2, 3, 4, 5. So the vector element 5, which is actually the 6th element, it has got the value 60 in it, and you can see that's been replicated across all the elements in V3. Now on the second one, register T3 is where we held the lane number that we wanted to extract. So that was a value of 3. So if we then look at vector index from V2, and we can see that the vector element, the index 3 is 400, and that's indeed what we have here. So, again, it starts from 0, 1, 2, 3, 4, 5, 6, 7, and so on like that. Let's have a look at this last vrgather command. And we'll look at register V5. So 100, 200, 300, 400, 500, 600, and 700. The reason for this is that when we looked at this one, we used vector V0, and vector V0 holds all the index values as well. So what we did was we took the values here of all these indexes in V2, and we replicated them. So because V0 had the value 0, 1, 2, 3, 4, 5, 6, 7, this is what we extracted from V2. Vector elements 0, 1, 2, 3, 4, 5, 6, 7. Which were here. And then these were simply replicated across here. So we can either extract a single element or we can do them all or whatever we wish to do. And let's just finish off with hitting next. And look at register T2. And hit register T3. So register T2 has got this value 60 because we extracted it from this register here, V3. And V4, we extracted it from here. So it took the first element, which was 60 and 400. And 400. So that's the vrgather instruction. This next instruction will continue with vrgather. We'll show a practical use where we can reverse the elements within a vector register. Let's run our code. The idea of this program is to reverse the instructions within a register. One thing that we've done here that's different from previous examples is we're going to use 16 elements for each vector register. So if we use 16 array members, then we get twice the number of elements, but these are going to be half the size. Now they're going to be in short or half word size, so they are still going to be 2 bytes wide, which is perfectly adequate for our needs. This allows us to process twice as many elements in a single pass. Hit Next. And then we're going to let A0 and A1 hold the address in memory where the vector 0 and vector 1 values have been defined. Now in our configuration instruction, T1, as we've seen already, holds 16. So the element size here is going to be 16, with a grouping of 1, and agnostic attributes. So we'll load up these vectors. Hit Next and we'll have a quick look at the vectors. So $v0.s this time instead of word. So this is for short or half word format. Then v1.s. So you can see the array here is 10, 15, 20, 25, and so on all the way up to 85. And in this one, we defined a set of index numbers that are backwards. Once we apply this, the idea is that it should put these elements into reverse form into a destination register. So if you look at vrgather, we're going to have v0 holding the index, which is here. And v1 is going to be our source holding these elements. We're going to put the result into v2. And again, .vv signifies vector to vector. Hit Next. And let's have a look at vector register 2. So what we see is that originally, we had vector register 1 with 10, 15, and 20, and so on right up to 85, and now we've reversed it. So this doesn't seem much, but if you had thousands of numbers and you want to reverse them all, then all you would have to do is reverse the indices here in v0. And then when it processes vrgather, it would process the values in the registers, in reverse order. So we could group a number of these registers together. We could make the element size as bytes if the values are small enough. In summary, we could very easily change hundreds, if not thousands of elements. So that's a practical use for vrgather. This next program will show us how to group 2 vector registers together. We will treat them as one when we perform instructions. So when we want to do adds or anything like that, we just refer to the first member of the group. Now, we'll start our program. In our configuration instruction this time, we're going to load 16 elements, but they are going to have an element size of 32 bits each. And the reason we can do this is because we're going to group them into 2. So we really only have 8 elements for each register, but because they are grouped as 2, we're going to treat them as 1. And this allows us to use 16 elements spanning the 2 registers together. So, Let's load up the datasets into the memory location pointed to by T1, first of all. And we're going to load that into the vector group, started by V0. So we just use one instruction here, and this is accessing register V0, but it will automatically put data into V1 as well. So let's have a look at V0. We see the data and it's here. And the other part right here. So, again, the point is we only addressed it by one register, but it actually filled the two because they are part of the same group. We always address it by the first member of the group or the lowest number down. Next thing we'll do is load in the dataset into the memory location pointed to by T1 again. And we'll do a similar instruction. This time, the group is V2 and V3. So let's have a look at register V2. And let's have a look at register V3. Okay. So there's our members there. Now what we're going to do is execute a vector immediate add. We're actually going to add the number 2 to all array members, and this is an integer value. Next, look at vector register V0. And we can see we've added 2 to each of those members. We can see the same thing for the partner as well. Finish off by doing the similar instruction for V2. So we can see that we've grouped 2 registers into one entity. We could also group them into 4 and 8, and this is very useful. It increases our productivity. So, really, where it would have taken us 2 sets of instructions to address 2 registers, here, we can do it with just one. This program is going to use a mask so that we can selectively get elements from different vector source registers and merge them into a destination. The mask will use binary values to decide where to pull the elements from. The graphic should help to solidify this concept prior to a GDB session. We'll set our configuration registers as before. By now, you should be familiar with this. So T0 will contain our AVL request. Element size is 32. No grouping, and agnostic attributes. Let's load the odd numbers. Set up register A1 with the memory address of the odds, and we're going to load those numbers held in the memory pointed to by A1 into vector register V1. Then we do the same for the even numbers. And we're going to set up the mask register. First, we'll do a load immediate into register T1, and then we'll transfer that into vector register V0. Now we'll have a look at the bit mask in V0. The T here incidentally stands for binary, so bits really. And then this is just a single array element where we have our mask. And you can see that's the checkerboard pattern. Let's have a look at the other registers V1, and we'll look at it in Word format. And we'll look at V2, also in Word format. And now we're going to select elements from these two vector registers according to whether the corresponding bit mask position contains a 1 or a 0. So hit Next to execute the vmerge command, and there's our destination register with our two source registers and the bit mask. Now let's have a look at vector register V3. And you can see the way it works. We've taken this element here from vector register 1. We've taken the second element from vector register 2. We've taken the third element from vector register 1 and so on all the way back. As an exercise, you should modify this program slightly just to make sure that you follow the way the vmerge instruction works. The preceding graphic will help to associate the mask bits with the source register's elements. We have already discussed vector configuration in some detail. Now we're going to cover this in more depth by introducing a concept termed strip mining. The RISC-V specification refers to strip mining as a method for handling a large number of elements using loop iterations. One disadvantage of a fixed vector length configuration, which is found in some other processor architectures, is the need to recompile if the registers become more capable. For example, assume that the vector registers have a fixed width of 64 bits and that the program configures these to use them as 4 16-bit elements. If within the same architecture, next-generation processors arrive with 256-bit wide registers, then to take advantage of this system upgrade, there would be a need to recompile the code. Now, RISC-V makes no assumptions whatsoever on the vector width. It doesn't matter whether its VLN is 64 bits, 128 bits, 256 bits, or even 1024 bits wide. It will automatically take advantage of this. And it does this because it doesn't make these assumptions on the width of the registers. It simply asks for an amount of elements, and if the system can give that amount requested, then all is well and good. If not, then it'll respond with how many it can provide. The request amount is the application vector length or AVL, and we have seen this is held in an integer register that is passed to the vsetVLI instruction. The quantity granted is reflected in the VL status register and also in the destination integer register, which is part of the vsetVLI instruction. The system will then look at this and say, well, okay. I wanted 16 elements but I could only get 8. That's not a problem, I'll just do another pass of a loop, but this time my AVL request will only need to be 8, since I have already processed 8 of my 16 elements. Or if we require 20 elements, there would be 3 loop iterations with the AVL requests being 20 for the first pass, 12 for the second pass and only 4 for the third and final pass. The RISC-V vector length is dynamic across processors. As of mid-2026, VLN is 256 on many systems. It may be that next year systems with a VLN of 1024 will be available, allowing the current systems to process 4 times as many elements with no code changes whatsoever. Next, we're going to show a number of programs, which is the best way to understand what's going on. Here's the first of our strip mining programs. In this case, we're going to square the first 20 integers. We've done this already using non-vector instructions. Alright. Let's look at our program. So the first thing we're going to do is set up our memory locations. They'll be pointed to by these registers here, A0 and A1. A2 is actually where we're going to hold the number of elements to be processed. So from this program, we want to process 20 elements in total. Register A2 will change its value as we run the program because we are going to use its count as our AVL value that will be passed to the vset VLI instruction. So let's hit next. Here we are in our vector loop, and if we type info register A2, we're going to look for 20 elements. So here, our AVL is 20. We are going to initially request 20 elements. These elements should be 32 bits in size. No grouping. And this time, we've left the tail elements undisturbed. We'll see what happens there later on. So hit next. And let's just have a look at the vector length register. So again, we asked for 20 elements here, but we have been granted 8 since the system's VLEN is 256. And that is also reflected here in register T0. So if you look at register T0, that'll be the same thing as register VL, the vector length status register. Alright. Let's load up V1 with the first 8 elements. And if we look at the second instruction, this is going to square those elements because it will multiply V1 by V1, putting the result in V2. Again, .VV is a vector-vector operation. So let's have a look at those vector registers V1 and V2. So you can see in V2 that these numbers are the squares of the elements in V1. Next we will store those numbers into memory for safekeeping. We do that with the vector store instruction, and they are going to be put in the memory location pointed to by A1, which is our array of all the squares. So now we want to subtract the value held in the vector length register, which is 8, and we're going to subtract that from A2. So originally, we wanted 20 elements. We processed 8 of them. Now we only need 12. So that's going to be our new AVL value amount. Alright. We're going to increment the memory source and destination locations accordingly, and we will branch if the AVL count is not equal to 0. Well, A2, we've seen up here, is not equal to 0. In fact, it's equal to 12. That's the remaining elements that we still need to process. So we're going to go back into our loop again. And there we go. So this time, we're going to request an AVL amount of 12 elements, and T0 will return the granted value, which again will be 8. So again, we can only process 8 elements at a time. Let's go around through the loop again. Let's just have a look at our new values in our vector registers. Remember, we already stored them in the memory location. It's no problem overwriting. There's the squares of let's carry on. Now if we look at A2, we only require 4 more elements. We're still not equal to 0. So we're going to enter the loop one more time. Alright. So our new AVL is 4. Let's hit that. We requested 4 elements. And we received 4 elements. So carry on with the loop. This time, we're going to find out after the subtraction that we have processed all 20 elements. We don't need to go into the loop anymore. We mentioned earlier that we were going to use the undisturbed policy for the tail elements, so TU here. So if we look at them, in the vector register, we can see the last 4 numbers are here, but the previous ones are left undisturbed. So in the previous second pass, vector 2 had these values in the elements. And now that we've run the loop again, we see that they've been undisturbed, whereas the other elements have been overwritten with the new values. So these 4 are the tail elements. Here's another strip mining program. We've modified the previous one to give us an element size of 16. So the question is, how many loop iterations are required? The next topic to talk about is stride. So a stride is defined as the byte-wide distance between consecutive memory elements during vector data loading or storing. The stride load and store instructions exhibit a similar format to the regular vector load and stores. The format for a strided vector load is VLSE with the element size in bits, followed by the vector destination register, the base memory address, and the stride amount in bytes. So remember, if you're going to be using words, then you need to use a value of 4. We use stride values with VLSE and VSSE instructions. The second S in the instruction signifies stride. We will show an example with a stride value of 8. Contiguous access is termed unit stride. This next program will use a stride value of 8, which is 2 words. Alright. We'll start off by loading a few registers. A0 is going to hold the address of where the values are that we want to square. A1 will hold the squared values that we just processed. We're going to process 20 elements. We will set up a stride count of 8 bytes, which is equal to 2 words. Set up the vector configuration. We're going to use 32-bit elements. And we will use a grouping factor of 1, and the elements will be agnostic. So the first action is that we're going to take is have a look at the words that we have pointed to by register A0. So here's all our words: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 of them in total. The next step is to multiply these numbers. So let's put them into vector 1 first. Now you can see that we've extracted just the odd numbers. So we have 1, 3, 5, and so on right up here. In total there are 8 numbers, and these are the odd numbers. That's it. We'll have a look at vector register V2. So now you can see here is that we've squared these values. 1 times 1 is 1. 3 times 3 is 9. Right up to 15 times 15, which is 225. Let's just have a look at the memory location pointed to by A1. Observe the 8 values, x8w. $A1. So you can see the values have been transferred from the vector register into the memory location pointed to by A1. Now we put these into consecutive memory locations. We could have put them in non-contiguous memory locations strided, but we are using contiguous here. We're just squaring the odd numbers and putting them into sequential memory locations. Alright. Let's hit next. We're going to do a little bit of register incrementing here so that our address pointers are correct. So let's just have a look at A1. So this has now been incremented to point to a higher memory location. If you look at A0, we're going to also be loading our numbers from a higher address in memory. Because T0 is not equal to 0 yet, and is actually 12, we have to loop again. 12 is the number of elements that we still have to process. We started off with 20 and were able to process 8 since we're granted 8 elements at a time. That leaves us with 12 to go. So let's hit next. We'll keep going until the loop has finished. So now we're out of the loop, and if I put in the original memory address where we were storing our data, note that the register content is now different because it's been incremented as we've gone through our loop, but this was the original starting address. So if we hit enter, you can see the memory locations, C8, D8, all the way right up to where we have the last square of 1521. Just as an aside, if we look at v2.w, you can actually see these last 4 elements here. And then these ones are the agnostic tail elements, and you note that they've been left at the same value. So that's the stride instruction. Incidentally, the companion book goes a bit further and shows a small example of many of the vector instructions used in conjunction with a small matrix inversion program. That wraps up tutorial 9 as well as this series of RISC-V tutorials. As I have mentioned during the sessions, the videos are a starting point and no more than that. A link to these tutorials and a freely downloadable companion PDF document is available online at the links shown. The RISC-V PDF is constantly updated and currently runs at over 300 pages in length. There is also a PDF on ARM64 assembly language and architecture. Hopefully the sessions will help anyone starting out with RISC programming. The material has come about from my own personal notes in a desire to educate myself with RISC-V and the ARM64 systems. If you find this useful, all I ask is that you spread the word. Thanks.